Dear students, today we will learn about the estimation of monthly average of daily diffuse radiation, then monthly average of hourly global radiation, monthly average of hourly diffuse radiation, and then global beam and diffuse radiation for clear skies, and then we will learn what happens to the tilted surfaces. Before we start our today's discussion, let us summarize what we have discussed in the last class. So, in the last class we have studied the need of the correlations for estimation of radiations. That means, we have studied the estimation of monthly average of daily global radiation and the classification of weathers, how these weathers can be classified like clear sky or cloudy skies, and then hazy, then partially hazy, all the informations we have studied, and also we have done the calculations of monthly average of daily extraterrestrial radiations. So, how this can be calculated, and finally, how this monthly average of daily extraterrestrial radiations can be used for calculation of monthly average of daily global radiation that was discussed in the last class. Let us discuss our today's topic on estimation of monthly average of daily diffuse radiation, followed by monthly average of hourly global radiation, then monthly average of hourly diffuse radiation. So, these three falls under cloudy skies. So, we will study the correlations developed by X-ray, which is suitable for estimation of hourly global beam and diffuse radiation under cloudless sky. Also, we will study radiation on tilted surfaces, which is very important because this is more practical. So, as we see the correlations for estimation of monthly average daily diffuse radiations, there are host of correlations developed by many researchers. So, as you can see, Liu and Jordan developed the correlations which relates monthly average of diffuse radiation to the global radiation, that is monthly average of global radiations is a functions of monthly average of daily global radiation to the monthly average of daily extraterrestrial radiation. So, it is a cubic expression. Okay. So, this sometimes you can represent as monthly average clearness index. So, we can represent KT is something like Hg bar by H naught bar. Okay. So, this gives monthly average clearness index. Okay. So, there are correlations where people have used this expression for representing monthly average clearness index. And the correlations developed by Modi and Sukhatme, this is something like HD by Hg. Hd is nothing but monthly average of daily diffuse radiation to the monthly average of daily global radiation is functions of Hg by H naught, that is monthly average of daily global radiation to the monthly average of daily extraterrestrial radiation. Okay. So, this is something like KT. Okay. This KT, that is monthly average. Also, Grand and Garg, they have developed a correlations of something like this. Okay. They have related this Hd by Hg as a function of S by S max. So, there are lots of correlations to estimate the monthly average of daily diffuse radiation. Okay. So, I would like to show the correlations which is available, some of the correlations which are extensively used for estimation of this monthly average of daily diffuse radiation. And for estimation of monthly average of hourly global radiations, so these correlations are reported to be used in many of the cases. So, AB values are given here, how this can be calculated. Also, one correlations developed by Liu and Jordan, this is something like that. Okay. So, this is ID is something like monthly average of hourly diffuse radiation, and this is monthly average of daily diffuse radiation. So, this part is known to us. So, finally, we can use these correlations for estimation of monthly average hourly diffuse radiation, and this is for monthly average hourly global radiation. So, there are a host of correlations available. So, what I have shown here, these are some of the selected correlations which is extensively used for estimation of monthly average hourly global radiation and monthly average hourly diffuse radiation. And as far as clearness index parameters are concerned, so there are certain cases like hourly clearness index, which is represented by KT. So, there is no bar on it, KT is equal to I by I naught, which is the ratio of hourly data of solar radiation in the terrestrial region to the hourly data of solar radiation in the extraterrestrial region. And the second case, sometimes daily clearness index is also defined by KT, which is equal to H by H naught, and which is nothing but the ratio of daily solar radiation in the terrestrial region to the daily solar radiation in the extraterrestrial region for that day. And finally, since we have already used this monthly clearness index, which is nothing but KT bar is equal to H by H naught, both the cases we have to put a bar. This is the monthly average of solar radiation on a horizontal surface in the terrestrial region to the monthly average of extraterrestrial solar radiation for that day. Okay. So, these informations are sometimes required as far as correlations in estimating daily global and diffuse radiations are concerned. Now, let us learn one very interesting correlations for estimation of radiation, that is global and diffuse radiation for cloudless sky, that is clear skies. Okay. And this is suggested by SRAE. SRAE is nothing but American Society of Heating, Refrigerating and Air Conditioning Engineers. They have developed a model of something like this. And here, before I discuss this, let us learn something this. So, as we already know, Ig is global radiation is sum of beam and diffuse radiation. Okay. So, this beam radiation we can write IBN cos of theta. Okay. So, this IBN is the direction of the this is the solar beam IBN, which is the ray direction, the intensity of radiation or solar flux in the direction of the solar radiation, and this angle is theta z. Okay. So, this is nothing but IB, which is IBN cos of theta z. Okay. As we know, Ig is equal to Ib plus Id, and we already developed what is Ib, then we can substitute Ib here in this equation, then Ig is equal to Ibn cos of theta z plus Id. Okay. So, this expression we are known now. Okay. Now, this SRAE has developed this model, and this Ibn is something like A, this is a constant. Okay. This value is defined for a particular month. So, for 12 months there are 12 values of A, people have already calculated, and of course, if we are very particular about the day, we can do interpolation and we can calculate the value of A, B and C. Okay. So, this is the correlations they have developed, and we can straightway use it for calculation of IBN. Once we know IBN, then we can calculate what is IB by using this expression, and once we know this IB, then we can substitute here. Also, we can calculate ID from here and we can substitute here, then finally, we can calculate what is global radiation, hourly global radiation falling on a horizontal surface. You should remember that this correlation is also applied for horizontal surface, radiation falling on a horizontal surface. Okay. But this is for cloudless sky. Okay. There is no cloud, it is on a clear day, right. So, these ABC values are constant, whose values have been determined on month basis. Okay. Why this is so? Because this weather is changing, and because in seasonal effect, and then sun earth distance is varying. Because of that, these values are varying. Okay. Let us see the variations of those values. So, for the case of January, its value will be 1201 watt per meter square, and B value will be something like this, C will be something like this 0.103, and then February it is 1183, then March 1164, That way, you can see the different values of this radiation. Okay. Suppose if I am interested in between, then we need to do say interpolation, then only we can correctly estimate the global radiation falling on a particular horizontal surface. Let us take an example. So, example goes something like this: estimate the hourly global beam and diffuse radiation at Guwahati. So, this is the latitude and longitude of Guwahati, and we are interested to know this variation between 10 to 14 hours local apparent time on May 15, 2019, and also compare this data with measured values given in the following table. So, measured values are given for global radiation and diffuse radiation. If we know this global and diffuse, of course, we can find out what will be the beam radiation, right. So, for calculation of this, if we write solution here, to what do you need? We need phi here. We explain how this phi can be applied. So, phi will be something like 26 degree 9 minute. So, this will be 26 plus 9 by 60. So, which will be equal to 26.15 degree. Okay. Now, phi is known, and delta, if we have to find out delta, already we know the equation 23.45. many times we have written this expression sine, then we have 360 by 365, we have 284 plus n. Okay. So, what is n now? N is May 15. Okay. So, then what we need to do? January 31, then we have 28, because 2019 is non-leap year. Then we have 31, January, February, then we have March, then we have April and May 15. So, if we add it, it will be 135. Okay. So, if you substitute this n here, then what you will get and do this numerical, and it will be 18.79 degree. Okay. So, delta will be 18.75 degree, and phi is already we have done 26.15 degree. Okay. So, these values are known to us now, right. Now, we need to calculate what is cos theta z. Okay. So, we already know this expression cos theta z is equal to, when beta is 0 and it will be induced out. So, sine of delta, then sine of phi, then we have cos of delta, cos of phi, then you have cos of omega. So, if we substitute those values delta and phi, so this cos theta will be a function of cos of omega. So, if we substitute this value, we will get sine of delta value is how much now? 18.79, and we have sine of phi is 26.15, then we have cos of delta is 18.79, then cos of phi is 26.15, then we have cos of omega. So, if we do the calculation, it will be something like 0.141956 plus we have 0.8498 cos of omega. Okay. So, this cos theta z we have evaluated now, it will be something like this. Okay. So, this omega, because in this case what we need to do, we need to take the average hours. Okay. And before we take the calculation, let us calculate the value of A, B, C. Okay. So, in our problem it is given in the month of May 15. Okay. So, if we go back to these slides, so it is May 15. Okay. So, in between, so April and May, right. these 2 months we need to consider. Okay, these 2 months we need to consider, and we need to do interpolation. Say for example, for 15 May 15, what we will do? So, we will use this and this for A. Suppose for A, what we will do? This is a decreasing trend. So, 1130 minus 1130 minus we will have 1106 divided by, we will have, it will be 30 days, then multiplied by we have it will be 24 days, right? It will be 24 days. Okay. So, if we do this calculation, then it is found to be 0.8 watt per meter square. So, this 30 is for this difference is 30, and then we will have 24. Okay. So, 24 is that that difference in days. Okay. That is 15 plus we will have 9. So, this 15 plus 9 is 24. Okay. So, that way you can calculate, and for similarly for B, what value we will get is 0.174. This is constant, there is no unit, and for C this value will be 0.128. Okay. So, 0.128, then 0.174, and then we have 1108. Okay. These 3 values we will consider in our case. Okay. Now, what we will do, since we have to calculate for 3 omegas. So, what we will do, we will take an average of this, maybe 10 to 11. So, as you know, omega, so the solar noon, this is solar noon, right. So, this may be at 12 o'clock, 11, and then we have 10, then maybe we have 13 hours, then we have 14 hours. Okay. So, this is 15 degree, okay, and then we have this is also 15. So, if I am interested to measure omega in between 10 and 11, then we will make at the center. So, it will be 15 plus 7.5, right. So, this will be 15 plus 7.5, and this will be 7.5, and this will be again minus 7.5, and this will be plus 15, sorry, this will be minus 15. So, this will be minus 7.5. Okay. So, these are the omega values, right. So, at different omegas we need to find out cos theta z. Okay. So, this will be, we have 22.5, right. This will be 22.5, and this will be minus 22.5. Okay. So, now if we substitute say cos of theta z at 22.5, this is omega, okay, degree. So, this will be in degree. So, I will write here as well, this will be in degree, this will be in degree, this will be degree, this will be in degree, right. Now, if we substitute this value, then this value is found to be 0.927, okay, and we can calculate for all the values. So, cos of theta z at 7.5, this is omega degree. Okay. So, this will be 0.9844, and same values we will get at minus 22.5 and at minus 7.5. Okay. So, these values will be same. Okay. So, cos theta z at this angle, cos theta z, okay, for minus 22.5 is again 0.927, and cos theta z at minus 7.5 is again 0.9844. Okay. So, we have calculated these values, and then what we need is IBN. So, already we know how to calculate this IBN, because we are familiar with the expression A exponential of minus B by cos theta z. Okay. So, we need to calculate for different cos thetas. Okay. So, we can use it for, say, for example, IBN at 22.5 degree of hour angle is equal to, A value is known to us, it was 1110.8 exponential of minus B. B is already we have calculated 0.177, and then cos theta z for this is equal to 0.927. Okay. So, if we do this calculation, then it is found to be 917.75 watt per meter square. Okay. So, we can convert it to kilojoule per meter square, okay, or maybe hourly. Okay. We can convert it by multiplying this into 3600. Okay. So, if we multiply this expression with 3600, then our unit will be kilojoule per meter square per hour. Okay. Then IBN at 7.5 degree hour angle will be 1110.8, then exponential of minus 0.177 divided by 0.9844. Okay. So, this will be equal to 928.01 watt per meter square. Similarly, if we are interested to get in terms of kilojoule per meter square per hour, then we have to multiply this expression with 3600. Okay, with 3600, then what we will get in kilojoule per meter square per hour, right. And these values are same for minus 22.5 degree for this, and then minus 7.5 degree of omega or hour angle. Okay. So, these values will be same, and we need to know what is ID. We can use the correlations developed by S-ray, this C into IBN. Since already we have calculated IBN, then we can substitute this value, and also we know what is the value of C, that is 0.130, and then we have BN is 917.75. So, where omega is equal to 22.5 degree or minus 22.5 degree, right. So, this will be equal to, this is equal to 119.30 watt per meter square. Okay. And similarly, for omega is equal to, ID is equal to 120.64 watt per meter square when omega is equal to 7.5 degree or minus 7.5 degree. Okay. So, since we know ID value now and IBN value at different angles, then we can calculate what is IB. Okay. So, next calculation will be IB. Okay. So, IB will be IBN cos of theta z. Okay. So, if omega is 22.5 degree or minus 22.5 degree, so value of IB will be 850.75 watt per meter square, okay, and IB value for when omega is 7.5 and minus 7.5, it will be 913.53 watt per meter square, okay, when omega is 7.5 or minus 7.5 degree. Okay. So, once we know this IB values, then finally what we can do, IG is equal to IB plus ID. Okay. So, now we got the two sets of values here. So, since no values of ID at 7.5 and minus 7.5 is same, similarly at omega value of 22.5 and minus 22.5 is same, okay, then we will get two sets of IG values. So, IG is IB plus ID. Okay. So, for when omega is 22.5 degree, then minus 22.5 degree, and then second case IG is for omega is 7.5 and minus 7.5 degree. Okay. So, this value is 1034.17 watt per meter square, and this value is 970.05 watt per meter square. Okay. So, now what we can do, we can generate this chart to compare the measured results and predicted results. So, these are the timing in between 10 to 11. So, we will have this omega, 11 to 12 we will have 7.5, then 12 to 13 minus 7.5, and 13 to 14 minus 22.5. Okay. So, global radiation which is measured is given here, and the estimated values are something like this. These are the estimated values. Okay. So, this unit is in the upper scale, it is unit is watt per meter square, and this is kilojoule per meter square, kilojoule per meter square is hour, okay, is hour, and this is watt per meter square, this is watt per meter square, this is kilojoule per meter square hour, and this is watt per meter square, and this is kilojoule per meter square hour. Just to show the calculation how this can be done, okay, since this is in kilojoule per meter square hour. Okay. So, similar things happens in case of beam and diffuse radiation. So, this is the measured values and this is the predicted values. This is the measured values for diffuse radiation and this is the predicted values for diffuse radiation. So, from this calculation, so what we can see, so if we see the beam radiation what is predicted by this S-ray model is higher predicted. Okay. So, measured was 2500, but it is a prediction is 3062. So, this is a higher prediction, and similarly in this case also when omega is 7.5. So, it is 2600, it is about 3289. Okay. So, in case of diffuse radiation it is under predicted, what you can see here. Okay. So, original value is 570, we are getting 434, that is under predicted. Okay. So, this is the reason why we cannot use a single universal approach or correlation for estimation of hourly radiations on a clear day. We need a location specific correlations for estimation of those radiation precisely, right, because this concentration of molecules in the earth atmosphere is not uniform, that is anisotropic, right. So, most of the cases isotropic distributions is considered for analysis. Okay. So, in this model exponential prediction model is used, that means that beam radiation when it travels, so it take care of that distance traveled by the beam radiation. Okay. So, summary of this problem is that, so we need a location specific correlation for estimation of radiation on a clear day. Okay. Of course, this is valid for other correlations developed for cloudy skies. Okay. So far, what we have discussed about the different correlations used for radiation estimation of horizontal surfaces. Now, we will learn how this solar radiation can be estimated in case of tilted surfaces. Okay. So, in order to find out the radiation flux on a tilted surface, we need to consider three parameters like beam radiation, diffuse radiation and reflected radiations. So, this is the exception for tilted surfaces. Okay. So, this earlier correlations were on the horizontal surfaces, now it is on tilted surfaces. So, certain beta will be there or tilt angle will be there. Okay. So, now we will learn how this flux can be estimated. Okay. So, here as I said there are three components like beam radiation, then diffuse radiation and reflected radiation. So, we need to define some kind of parameter called tilt factor. Okay. So, tilt factor for beam radiation, tilt factor for diffuse radiation and then tilt factor for reflected radiation. Okay. So, in case of beam radiation, how do we define it? See, this tilt factor is the ratio of beam radiation flux falling on a tilted surface to that falling on a horizontal surface. Okay. So, this is defined as tilt factor, right. So, this is something like if we designate RB as tilt factor. So, this is something like IB dash to the IB. Okay. So, this IB dash is nothing but IBN cos of theta z. Okay. So, theta here, okay, and then you have IBN cos of theta z. Okay. So, this is for horizontal surface. As you can see, what happens here, this is the perpendicular, when sun ray is falling, it is the perpendicular to the horizontal surface, and here in case of if radiation is coming this way and this is the angle. Okay. And if it is inclined, then it will be perpendicular to the inclined surface. Okay. So, this angle is theta and the earlier case it was theta z. Okay. So, in the horizontal surface theta and theta z are same. Okay. So, this IBN cos of theta and then IBN cos of theta z. Okay. So, this IBN is the intensity of solar radiation flux is same. So, we can remove this, then it will be finally the expression will be cos theta 2 by cos theta z, cos theta 2 cos theta z. Okay. So, cos theta is angle of incidence and theta z is a azimuth angle, right. So, if we consider beta, because a certain beta will be there because of this slope. So, this angle is beta. So, if we introduce there, then the expression will be something like this: sine of delta multiplied by sine of phi minus beta plus cos of delta multiplied by cos of omega multiplied by cos of phi minus beta to sine phi multiplied by sine of delta plus cos phi cos delta and then cos omega, right. So, if we know beta and other angles, then straight away you can calculate what is the tilt factor for beam radiation. Similarly, we can calculate the tilt factor for diffuse radiation, which is defined as diffuse radiation flux falling on a tilted surface to that falling on horizontal surface. Okay. So, this is how this tilt factor for diffuse radiation is defined. So, this expression is something like RD is equal to 1 plus cos of beta divided by 2. Okay. This is also known as radiation shape factor for the tilted surface with respect to the sky. Okay. So, what assumption is here, this sky is isotropic. Okay. So, even though this atmosphere is different at different locations, but they assume that this sky is isotropic and is diffused uniformly, diffuse radiation is falling on the inclined surface. So, why this inclined surface is so important? Because in most of the cases, these inclined surfaces are used for harvesting solar energy. Say for example, flat plate collector. So, we have to install it at certain angles, right. So, that is how this is very, very important, solar radiation on tilted surfaces. Okay. And then next parameter is reflected radiation. In case of reflected radiations, we will define this RR. So, RR can be explained something like rho multiplied by 1 minus cos of beta divided by 2. But here radiation shape factor is something like 1 minus cos of beta divided by 2. So, this is known as the radiation shape factor, okay, radiation shape factor of the tilted surface with respect to the surroundings or ground. Okay. So, because as you know there are three components, this is the additional components which is introduced here when we are interested to measure solar radiation on tilted surfaces. Okay. So, what happens here, we need to consider rho here, and also we need to consider or assume that our reflected radiation when beam radiation and diffuse radiation falling on the ground and it is reflected, right, it is reflected. Okay. So, it is assumed that this reflected radiation should be isotropic and diffused, okay, and this reflectivity need to be considered. Okay. When we introduce this rho, then and we use it here in this expression will be something like this, and this is nothing but tilt factor for reflected radiation. Okay. So, now when we are interested about flux on tilted surface, then we have to follow this expression, and which is coined by Liu and Jordan. Okay. So, this is IB is the beam radiation intensity, ID is the diffuse radiation intensity, and RV is the tilt factor for beam radiation, RD is the tilt factor for diffuse radiation. Then this IB plus ID, which is nothing but global radiation, multiplied by RR. This RR is nothing but tilt factor for reflected radiation, right. So, now what I am interested is about the ratio between this flux on tilted surface to that on horizontal surface. Let us see what happens there. So, let us see this Ig is the flux received by the surface, received by the horizontal surface, received by a horizontal surface. Okay. Now, as we already defined what is IT, IT is nothing but IB multiplied by RB, then we have ID multiplied by RD, then we have IB plus ID in bracket, then multiplied by we have RR, right. And also we know what is IG, IG is nothing but IB plus ID, right. Now, if we go back to the earlier slides, maybe we can name this as equation 1, and this may be equation 2, and this may be equation 3, and finally, this may be equation 4, right. Now, if we take this may be equation 5, okay. So, this expression already we know. Now, if we make something like I t by I z, then what will happen? Okay. So, this I b divided by I z, then we have R b plus I d, then we have I z, then R d plus I b plus I d to I z, then we have R r, right. So, since we know this I b plus I d is I z, okay, so we can get I z by I z is 1, and here I b is nothing but I z minus I z. So, this I b will be I z minus I d, right. So, if we divide this by I z, then what will happen? This will be 1 minus I d by I z. Okay. Then we have R b plus I d by I z, then we have R d plus this will be R r, right. So, this will be equation number 6, right. So, this equation says that the total radiation received on a inclined surface to the horizontal surface, right. So, sometimes what happens, we might be interested to investigate this daily or say what is called monthly average of hourly radiation flux, which are interested sometimes. So, that can also be calculated. Okay. So, if we, so this equation, what I mean to say, so this equation will give instantaneous solar radiation flux, and same equation can be used for if we are interested about hourly radiation, right. But sometimes we are interested to estimate the radiation on average basis, maybe monthly average of hourly radiation flux received by the inclined surface. Okay. So, under that condition, what we will do, we will put a bar on it, okay, here, and then we will have 1 minus I d by I z, this is bar, and of course, we need to use R b bar plus I d by I z, we will put a bar on it, then R d, and we have R r. Okay. So, this may be equation 7, and this will give monthly average of hourly radiation, okay, and this will give hourly radiation, hourly. We should keep in mind that if we are calculating for hourly, and then if we consider maybe 10 to 11 o'clock, then at the mid of the time we need to consider for maybe 10:30, we need to consider for evaluation of omega or hour angle, that we should keep in mind. And this expression is for monthly average of hourly radiation, okay, that is total radiation flux received by the inclined surface, right. And on the top of it, sometimes the researchers are interested to know how daily variation of solar flux is varying, or so daily variation is required for some kind of calculations. Okay. So, if this is so, then what we will do? We will just use H t and H g, right, and this is for daily. Okay. So, daily this flux which is received by the inclined surface. So, that can be calculated by using this expression. So, this will be something like 1 minus H d by H g, sorry, this is not required, and this is R b plus H d by H z, then we have R d plus R, this is R. Okay. So, this is 8. So, now how to calculate this R b? So, this is till factor for beam radiation when we are interested for daily radiation flux. Okay. So, how to do that? We need to integrate this over timing, right. So, that earlier equations, so already we know R b is cos theta by cos of theta z, okay, and expression is also known to us. Okay. So, this cos theta expression is something like sine of delta, then you have sine of phi minus beta here, okay. Then we have plus cos of delta, cos of omega, then we have cos of phi minus beta, okay. So, if we make this integration and then it will be dt, right. And here it will be sine of delta, then we have sine of phi, then we will have cos of delta, cos of omega and cos of phi, okay, and this will be in dt. Already we know this t, because 15 degrees 1 hour for our angle calculation, omega by 15 into 180 by pi, okay. So, this will be something like 12 omega by pi, and this dt will be 12 by pi into d omega, okay. So, using this, in this equation we can, what we can get? We can change the integer and we can integrate from minus omega s to plus omega s, okay, omega minus omega to plus omega. So, this is for sunrise, so W s is for sunrise and sunset, okay, for inclined surfaces, and this is for horizontal surfaces, okay. So, if we substitute here and do the integration, then what we will get? So, here this part will be constant and then we have only 2 omega s. So, this 2 will come out, okay. So, this 2 will come out and then we will have 2 omega s, we have sine of phi, then sine of phi minus beta plus. So, here integration, this will be the variable and these two are the constant. So, sine integration of sine is cos omega is sine omega, okay, and then it will be plus omega to minus omega. So, it will be 2y cos of delta, then sine of omega, and we have cos of phi minus beta, right. And here same thing will happen, 2 into omega here, sine of, sorry, this is not phi, this will be delta, sine of delta, then sine of phi, then we will have 2 into cos of delta, sine of omega, we have cos of phi, right. So, this 2 is common, this 2 we can take common, okay, we can take common here and we can rub this and this will be something like this, and again we can take this and we can rub this. So, finally, what we will get? RB is omega s multiplied by sine of delta, sine of phi minus beta plus cos of delta, sine of omega. So, this omega will be omega s and cos of phi minus beta, and here sine delta into sine of phi plus cos of delta, sine of omega and cos of phi, right. So, this omega s is for sunrise or sunset when the surface is tilted, and this is for horizontal surface. This omega s stands for horizontal surface, right. So, this RB can be calculated by using this expression, okay. And what about RD? So, RD will be something like same only 1 plus cos of beta, this will not change, only it will vary with respect to, but for other case for RB, so depending upon the inclination, that expression will vary. So, R will be 1 minus cos of beta multiplied by rho divided by 2, right. And this expression is for daily. Sometimes it may so happen that a researcher want to know how this monthly average of daily radiation is varying. So, under that condition what we will write? So, that expression will be h t by h g is bar on it, and then we have 1 minus h d by h g, then we have r b plus, then we have h d bar to h g bar, this is r d, then we have r r, this is bar. Okay. So, this r value, so this r b dash will be r b on a representative day, and this r d bar is equal to r d, and r r bar is r r. Okay. So, what we understood by using this expression, what we can calculate is the monthly average of daily radiation flux received on a tilted surface. Okay. So, these different conditions we need to understand, then only we can calculate as per our requirement. Okay. So, let us take one example to strengthen our understanding on calculation of say monthly average hourly radiation falling on a flat plate collector. Okay. So, we will discuss those flat plate collector when we study solar thermal systems. So, this will be installed at a certain angles. Okay. So, if we consider this is a flat plate collector, this will be installed at certain angles. Okay. So, always we need to maintain that, right, and of course, this angle will be different for different cases or different locations, right. So, now let us solve this problem. So, this example goes something like calculate the monthly average hourly radiation falling on a flat plate collector, okay, and this facing is due south. Okay. So, if it is facing due south, then gamma is 0, it is obvious. We have discussed this matter why gamma is 0, and slope is 26 degree. Okay. Then given that there is something like location is New Delhi and October. So, when we say month October, so we should consider 15th of October, 15th of as per Klein's recommendation, right, and the time is given as, so we need to find out the radiation in between 11 to 12. So, we will consider means 11:30. Okay. So, reflected radiations rho is 0.2, normally this is considered for glass surfaces, and Ig value and Id values are given to us, right. So, what we need first, we need to know what is n. Okay. So, we know how to calculate n. Okay. If we start from January, so it is 31, okay. Then we have 28, then we will have 31. So, January, February, then March, and then we have April, then we have May, then we have June, July, August, then we have September, then we have October 15. Okay. So, this is October. So, if we add it, then this is found to be 288. Okay. So, this n is known to us now, this is 288, right. So, once we know n, then what we can calculate? We can calculate declination, delta is 23.45. Okay. The sine of, we have 360 to 365, and we will have 284 plus n. Okay. So, this n is now 288. Okay. So, if we substitute it, then what we will get? It is about minus 9.599 degree. Okay. So, something like this. Okay. Now, since we know n and delta, and what we need again, it is phi. Okay. So, what will be phi? This 28 degree 23 minute. So, it will be 28 plus 23.60. So, which will be equal to 28.38. Okay. So, this will be in degree. So, now we know phi also, right, and once we know delta and phi, then we can calculate what is R b. Okay. So, R b we can calculate. So, R b, already we know the expression, sine of delta I am writing again, sine of phi minus beta, then we have plus cos of delta, cos of omega, then we have cos of phi minus beta, and then we have sine of phi, sine of delta plus cos of delta, then we have cos of omega, then we have cos of phi. Okay. And then what is omega here? We have not done this. So, omega will be 7.5 because this is solar noon, okay, and every 1 hour is 15 degree. So, if it is 12 o'clock and this is 11, so this is 15 degree. So, as we said, since we need to consider in between these two, then it will be 7.5 degree. Okay. So, omega is 7.5 degree for this case. Okay. So, we substitute the value of delta, phi, beta and omega, and we will get a value of R b is equal to 1.242. Okay. This is R b. And R d value we can calculate. How we can calculate? Already we know 1 plus cos of beta divided by 2. Okay. So, beta is known, this is 1 plus cos of 26 degree divided by 2. So, this is equal to 0.94393. Okay. So, this is nothing but R d. Okay. So, R d is also known. Now, we will calculate what is R r. Okay. So, R r is nothing but 1 minus cos of beta has to be multiplied by rho divided by 2. This is equal to 0.0101. As you can see, this contribution of R r is very less. Okay. So, reflected radiation is very less. So, most of the cases this can be discarded, but no, if no reflected radiation is somewhat significant, then of course, we need to consider this. And now, we will apply our that relationship for calculation of monthly average of hourly radiation for these tilted surfaces. So, expression was something like I t, then we have I z. So, we will put a bar because since it is monthly average of hourly radiation. Okay. So, this is something like that, then this will be 1 minus I d by I z, put a bar, then we have R b, then I d by I z, then we have R d, then we have R r. So, what happens in this case? This R d is equal to R d bar, this is nothing but R d bar, and this is nothing but R r bar, and on representative day this is nothing but RB bar. Okay. So, we can utilize these values and we can do the calculations now. So, this will be something like 1 minus, so ID and IG values are given. So, it is 986 divided by 2350, and then we will have RB is already calculated, this is 1.242, then we have ID 986 2350 multiplied by, we will have 0.94393 to be precise, and we will have 0.0101. Okay. So, if we do these calculations, it is found to be 1.1261. Okay. So, since Ig is known to us, then we can calculate the radiation what is received on the inclined surface, okay, which is 1.1261 multiplied by Ig value is 2350, which is equal to 264644 kilojoule per meter square hour. Okay. So, this IT value is calculated to be 2646.44 kilojoule per meter square hour, right. So, this is the procedure by which we can calculate the radiation flux received on a inclined surface. Okay. So, there are numerous conditions may arises for calculation of this IT bar or maybe HT bar. Okay. Accordingly, that researcher should decide the kind of correlations to be used for estimation of radiation, right. So, let us summarize what we have discussed in this lecture. So, we have studied different correlations for estimation of monthly average of daily diffuse radiation, monthly average of hourly global and diffuse radiation on horizontal surfaces and cloudy skies. Also, we understand how we have calculated H naught bar for those cases for estimation of all those radiations, and we have studied correlations for estimation of hourly global beam and diffuse radiation on horizontal surface when sky is clear. Okay. So, under this condition we have studied X-ray model. So, American Society of Heating, Refrigerating and Air Conditioning Engineers, they have developed correlations for estimation of hourly global beam and diffuse radiation on a clear sky, and which is applicable for horizontal surfaces. Okay. So, in this case what we have studied, so here IBN can be expressed something like A into exponential of minus B by cos of theta z, because it is horizontal surface. So, this should be always cos of theta z. Okay. This A and B values were calculated from a chart which is available for monthly basis, and this ID was calculated something as C into IBN. Okay. So, this IBN is known to us because this is the radiation flux which is coming from the sun in that direction. So, suppose this is something like this, this is the IBN, okay, direction of the sun ray. And also we know this Ig is equal to IB plus ID, okay, and this IB is nothing but IBN cos of theta z and ID. So, once we are done with IBN and then ID, then we can use this relationship for estimation of global radiation. Okay. Also, we have concluded by solving a problem that this correlation is overestimates the beam radiation and underestimates the diffuse radiation. So, we need some kind of correlations for location specific correlations we need for estimating this radiation correctly. Okay? And then finally, we have learned how we can estimate the total radiation which is falling on an inclined surface. Okay? So, there are many cases, maybe instantaneous cases, maybe hourly, or maybe monthly average of hourly, or maybe daily or monthly average of daily. There are different conditions which may arise based on the situations. So, all the conditions we have addressed in this lecture, and also we have solved numerical problems to strengthen the understanding on the topic. Okay? So, thank you very much for watching this video.